All right, so welcome to the last video of my Introduction to Mathematica within Calculus 3 here at Mississippi State University. Over the past 6 videos, I've kind of introduced the basics of Mathematica with more of a lens going towards the Calculus 3 course that I teach at Mississippi State University. So in this last video, we're going to cover one more topic that we covered during lecture, and that is the idea of Taylor and or Maclaurin series. So I'm going to show how that works within Mathematica. And so as you learn that material during the lecture, you can come and watch this video and it can guide you how to approximate and how to do these types of series within the Mathematica system. So one more time, let me share my screen here. And so we have our normal notebook file that I've been using for every video so far. And so with Taylor or Maclaurin series, the idea is that we are trying to take a function and create a polynomial approximation to be as accurate as possible. But during the lecture of the class, I go through the details of the formula and all that good stuff of how to develop it. And we talk a lot about how you need more and more terms. And as you add more and more terms, you can get more and more accurate. Let me show you how we do Taylor series within Mathematica. So in Mathematica, we are going to use a built-in function called, well, series, which is really nice in this case. So we are going to click on series and use our double down arrow. And what we're going to do is we are going to generate, and it says we're going to generate a power series expansion of the form x minus x naught to the n. Well, as you might recognize during lecture, we first started by talking about power series and then slowly transitioned into the idea of Taylor series. So this is exactly what we want to do. So I'm going to click on that, right? And then we are going to ask Mathematica to create a series of whatever function we would like. So what I'm going to do is I'm going to do a cosine function for the first one. So we're going to do cosine of x, all right? You have to tell Mathematica what your variable is. So obviously for us, that would be x. When you get to the x naught piece, this is asking you for the center of your power series or your Taylor series. So whatever center you're trying to use, if it's Maclaurin, that would be 0. If it's some other value, which we usually call a during lecture, you would put that in the x naught spot. So for this example, I'm going to do pi divided by 4. So pi divided by 4. And then in the end spot is you are telling Mathematica how many terms you would like to try to generate for the Taylor series of cosine of x. So I'm going to start very small to begin with. So let's just start with 3. And so I'm going to go to the end and I'm going to have Mathematica input this. All right. And so as you can see, it generates a cosine approximation at pi over 4. Now, one thing you will notice, and it's going to look a little bit weird, is at the very end, it is adding what they call an order expression. This is essentially saying that if you were to go one step further, Mathematica or Taylor series in general could be used to find a fourth order. The problem is that for what I'm going to ask y'all to do on your project, you do not need this order term in here. So the question is, how do we get rid of that? Well, what I'm going to do is I'm going to go back to the series function that we just used, and I'm going to add an extra function around it. So we're going to use the idea called normal. So all you need to do is type the word normal with a capital N, open a bracket, and then go to the very end of your code and close your bracket. This should not change anything that you're doing as far as the answer goes. It should just drop that order term off of the end. So if I input this again, you see, it's the exact same answer, only without the order term at the end. And you can do this for as many terms as you want. So if we wanted to go to a fourth term, if I wanted to add one more term there, I would just change my n value to 4, re-input, and it will continuously add on terms. Now, as you might have recognized during lecture, I typically keep this to 3 or 4 terms because doing this by hand is very tedious and time consuming. And so I don't want you to waste a lot of time doing that. Instead, we're going to have Mathematica do something that we normally wouldn't do. So I'm going to go to 10 terms, which I would never have you do by hand, but Mathematica can compute it pretty quickly. So what this is this is a Taylor series approximation of cosine centered at pi over 4 out to the 10th degree. And then what we discussed during class and what our claim was is that the more and more terms you add, the more and more accurate you get for a Taylor approximation to the original polynomial. So what I'm going to task you all with doing is to show me how accurate this actually is. So to do that, I first want to graph the two functions to see how close they are to each other. So what I'm going to do is I'm going to label two functions here. I'm going to label what I'm going to call P1, where I'm going to have Mathematica plot. Remember this from a previous video. We are going to plot the original function I'm taking the Taylor series of. So I want to plot cosine of x with a variable of x. And let's just go from, for right now, -5 to 5. And we can always change that in just a minute. So that's going to be my P1 plot. So there's your cosine wave. But now what I want Mathematica to do is to also graph the Taylor polynomial that I just created. So I'm going to do a very similar code. I'm going to plot and use that first function. And then since this is pretty ugly, don't try to type all this in by hand. I would just highly recommend you highlight whatever it is. And we're going to paste that in for our f function. And then just to keep it similar, I'm going to do x is still my variable. And we're going to go from -5 to +5. And I'm going to have Mathematica draw that. You can already tell that they are pretty close to each other just by visual representation. But let's put them on the same graph to see what it actually looks like. So I'm going to use another built-in function we discussed in a previous video, which is show. And I want Mathematica to show me the P1 graph and the P2 graph at the exact same time. And so I will do that. And as you can see, they are pretty darn close to each other. As we're moving along, you can hover over and you can see how accurate this is as you're moving along through your terms. It's so close to each other that until you get beyond really the -2, really to +3 range, there's not much difference at all. And that's the purpose of what Taylor series is doing. Just by going to the 10th degree, I have gotten a very, very, very good approximation here. So now my question for you all is going to be, well, how accurate is this? So a number that I picked out is x equals 3. So if you go to the first graph of the cosine function or even the non-cosine, if I go down to 3, I am curious, and you can go to the combo graph as well, it looks like those graphs are the same thing, but are they really the same thing? So here's what we have to do to check that. I need to evaluate not only the cosine graph, but I need to evaluate this long Taylor polynomial in order to do that. So here's maybe the most direct way to get it done without overcomplicating it too much. So step number 1 is I'm going to go back up to the Taylor series that we created on step number 1. So I've already shown you how to do that. Now I actually want to call this a function. That way we can evaluate it. So I'm going to let this be my f of x function. It's not going to change anything in your code and your output. All it is it's letting me now call this f of x. So let me shift enter there. You see nothing changed, but at least Mathematica now knows what f of x is. If I go down a little bit lower, I'll go back down here to the bottom of my code. I'm going to do g of x is equal to cosine of x. That one's a little bit easier just to retype back out, so that's why I went ahead and just redid it here at the bottom. So g of x is cosine. My question is, what is f of 3? So if I were to plug 3 into that Taylor series polynomial, I would get an answer that looks like this. Now, that's not a very good representation because honestly, I have no idea what that is. So I'm going to do capital N of %, and we get a decimal approximation of -0.99012. How close is that to the g of x, which is the original function cosine? So I'm going to do g of 3 as well. It's going to give me an exact answer, and I am going to do a decimal approximation, which is -0.989992. And so as you can see, these two approximations are very, very close to each other. They're so close that if they're only off by really, it looks like a 100th, but really it's smaller than that because you've got 9992 here on the end. So that's the last thing we want to make sure we can do. How close are these two functions really to each other? So I'm going to take the bigger number, which in this case is the actual g of 3. And actually, we can just use our absolute value function here, which is ABS. I'm going to take g of 3 minus f of 3, just subtracting the two values, all right, which is going to give me some number like this. And then I'm going to once again do my n%. And you see, it takes the absolute values so you can get the actual error. This is how far they are off. They are 10th, 100th, 1000th. You have 12 or 1/10,000th of a difference. That is very, very marginal. And keep in mind, that's only with 10-degree polynomial. As we discussed during lecture, you could go all the way out as far as you want to. So for example, and I'm not going to do this all the way back out again, but if we were to add more and more terms to these, we would get a more and more accurate representation. So much so that if you were to go all the way out to the infinite term, you would actually get the exact answer without any error at all. And so what this shows in Mathematica is that Mathematica can calculate a Taylor series or a Maclaurin series very quickly. It can calculate a very high degree of these two series, and it also allows us to then use our skills we've learned in previous videos. We can plot the Taylor series function and the original function on the same graph. I showed y'all how to do that. Then we also talked about how to evaluate each of those functions. And then here at the very end, we discussed how to calculate the error between the two values that we found. And remember, this should be a relatively small number. If it's a large number, then that means you probably picked a number very far out from the center of a graph, and that's why it's not as accurate at that point. Especially with things like trig functions, it takes a lot of terms in order to get a perfect approximation as you move away from the origin in this case, or x equals 0. And so that's actually the last thing that I want to teach in my introductory videos for Calculus 3. So over the last 7 videos, you have seen a lot of stuff done within Mathematica. All of these topics build upon themselves. And honestly, there's a lot more topics we could cover, but I tried to keep it very bare so that I'm not overcomplicating anything or throwing information at you that is not necessary. I highly encourage anybody watching these videos to explore further within Mathematica and see the different capabilities that it has. There are things beyond what you will ever need built into this system. So as you're working on your project and you're getting ready to turn it in and just double checking that everything is accurate, refer back to these videos. The YouTube channel I have here will always be active. If you go to another class and you need to re-watch some of this information, it will be here for you to come back and watch. I hope you've enjoyed these last 7 videos. You can subscribe to my YouTube channel. And like I said, I have all kinds of lecture videos and different Mathematica videos for different disciplines. Have a great day.